Marine shells have been found thousands of meters above sea level in the Himalayas. Limestone at the summit of Mount Everest formed as seafloor mud. Entire mountain ranges are built from compressed ocean sediment. 200 million years ago, a tropical ocean stretched between Laurasia and Gondwana. It covered what is now Europe, North Africa, the Middle East, and large parts of Asia. It existed long before the Atlantic fully opened. Coral reefs expanded across its shallows. Ammonites multiplied in immense numbers. Marine reptiles moved through waters that shaped global circulation and climate. This ocean influenced monsoon systems. It redistributed heat across continents. It connected coastlines that are now divided by deserts and mountains. Geologists later gave it a name, the Tethys Sea. It lasted longer than the dinosaurs. And then, over millions of years, it narrowed, its seafloor bent, its sediments folded upward into ranges that now define national borders and skylines. Today, there is no obvious ocean in its place, not drained, not dried, not frozen, raised into stone. What force can compress an ocean basin into the Himalayas? How does a body of water that once controlled climate patterns disappear so completely? And if the Tethys Sea could vanish, what does that say about the permanence of the oceans we know today? Tonight, we follow the rise and disappearance of the Tethys Sea across deep time. We examine the evidence written into mountains. But before we begin, I'd love to know where you're listening from tonight and what time is it there. It's always a joy to see how far these sleepy stories drift across the world. And if these gentle journeys bring you peace, a like or subscribe helps others find their way here too. Now, let your breath slow, let your body settle, and together we will trace the memory of the Tethys Sea preserved in rock. Before any familiar shoreline existed, the planet carried a different geometry, a vast continental body stretching almost from pole to pole, its interior dry and immense, its edges washed by a single encircling ocean. The landmass we now divide into separate names rested together in one immense union, a structure geologists call Pangea, assembled over hundreds of millions of years through earlier collisions and closures. Its scale altered winds and currents, drawing moisture toward the coasts while leaving the deep interior exposed to extremes of heat and seasonal drought. Mountain belts stitched its seams, and rivers wandered across distances that no longer exist on modern maps. By roughly 200 million years ago, the quiet strain beneath this supercontinent began to express itself. Heat from the mantle rose slowly upward, thinning the continental crust along zones of weakness inherited from older sutures. Fractures formed not as sudden tears, but as widening scars, valleys deepening over spans of time that exceeded entire biological epochs. Within these rifts, basaltic magma welled upward, cooling into dark sheets that marked the earliest stages of separation. The northern portion, later known as Laurasia, began to ease away from the southern lands of Gondwana, though at first the movement measured only centimeters across a year, imperceptible to any living creature. As the crust stretched and subsided, shallow basins formed between the diverging blocks. Water from the global ocean advanced into these low regions, pooling, warming, and gradually linking into a continuous seaway. This was the early Tethys Basin, positioned in tropical latitudes, where sunlight fell intensely and evaporation cycled moisture back into the atmosphere. Over time, continued seafloor spreading generated new oceanic crust along nascent ridges, pushing the continents farther apart and allowing the basin to widen. The space that would one day hold the Atlantic had not yet opened. Instead, this tropical corridor served as the principal marine gateway between east and west. Global sea levels during much of the Mesozoic remained higher than today, in part because the absence of extensive polar ice caps left more water in circulation, and in part because the youthful oceanic crust created by active spreading stood buoyant and elevated, displacing seawater onto continental margins. Warm climates prevailed across wide latitudes, softening temperature contrasts between equator and pole. Atmospheric circulation patterns differed subtly from those of the present, shaped by the arrangement of land and sea and by the distribution of heat across this broad equatorial ocean. All of it unfolded through motion so gradual that mountains rose and seas expanded without spectacle. Plates drifted with steady persistence, guided by convection currents far below the surface, rearranging coastlines and climates over spans that dwarfed individual species. In that slow reconfiguration, the early Tethys took form, not as an anomaly, but as a natural consequence of Earth's restless interior, a luminous band of water dividing the ancient world, long before the Atlantic began its own quiet widening. Beneath the broad tropical waters that had begun to gather between separating lands, the crust itself was thinning, drawn apart by forces rising slowly from the mantle. Heat accumulated along linear weaknesses, lifting and stretching the overlying lithosphere until it fractured into parallel faults. Valleys subsided between these faults, forming elongated troughs where magma ascended in pulses, cooling into fresh basalt as it met the sea. What had begun as continental rifting matured into true ocean basin formation, a transition measured not in moments, but across millions of years of persistent divergence. As separation continued, a mid-ocean ridge established itself along the axis of spreading, a submarine mountain chain where new oceanic crust formed continuously. Molten material welled upward, crystallizing into dense dark rock that contrasted sharply with the lighter granitic composition of the continents on either side. Continental crust, thick and buoyant, resisted subduction and carried the memory of ancient collisions. Oceanic crust, thinner and richer in iron and magnesium, moved outward from the ridge in symmetrical bands. Magnetic minerals within that cooling basalt aligned with Earth's field, quietly recording reversals in polarity and preserving a striped archive of expansion across the seafloor. The young Tethys widened as this process repeated, its floor renewing itself, while its margins defined new coastlines along Laurasia to the north and Gondwana to the south. In its earliest configuration, the basin stretched in an immense arc across equatorial latitudes, open toward the vast Panthalassic waters, and linked to adjoining seaways that allowed currents to circulate freely. Positioned within the tropics, it absorbed abundant solar energy, its surface waters warmed year-round, its evaporation feeding atmospheric circulation that drifted moisture toward nearby continental margins. Shallow continental shelves fringed much of the basin, their gentle slopes illuminated by clear water. There, carbonate sediments accumulated as shells, skeletons, and microscopic plankton settled layer upon layer across the seabed. Coral frameworks began to establish themselves in stable zones, constructing reef complexes that buffered coasts and created intricate habitats. Ammonites and other marine organisms navigated these warm shallows, their forms adapting to salinity gradients, temperature stability, and the interplay of tides along broad platforms. Farther from shore, the deeper portions of the basin remained in quiet motion, currents redistributing heat between connected oceans, integrating the Tethys into a global system rather than isolating it. The geometry of the continents guided these flows, shaping pathways that would influence climate far beyond the basin itself. All the while, seafloor spreading continued with steady persistence, adding width to the ocean and carrying older crust outward toward its eventual descent. In this balanced cycle of creation and movement, The Tethys did not appear suddenly, but emerged as a natural expression of tectonic rhythm, a luminous equatorial ocean born from separation and sustained by the enduring mechanics of Earth's interior. Light filtered downward through warm equatorial water, illuminating broad shelves that sloped gently from the surrounding continents into the open basin. In these shallows, life gathered not in scattered isolation, but in dense, interlocking communities built upon calcium carbonate and patience. Coral colonies anchored themselves to firm substrates, their polyps extending delicate tentacles into clear currents rich with suspended nutrients. Over generations, skeletons accumulated layer upon layer, forming rigid frameworks that resisted waves and shaped the coastline into intricate barriers and lagoons. What began as individual organisms became vast reef complexes, visible even from distant horizons as pale ridges beneath the sunlit surface. Around these reefs, carbonate platforms expanded outward, constructed from the skeletal remains of countless marine creatures. Mollusks, echinoderms, and microscopic plankton contributed shells that settled as fine sediment, compacting into thick accumulations across the seafloor. The water remained transparent, low in terrestrial runoff, allowing sunlight to penetrate deeply and sustain photosynthetic symbionts within coral tissues. This steady exchange of light and nutrient flow created conditions of remarkable productivity where ecological niches multiplied and species diversified within confined but stable environments. Ammonites drifted through these waters in elegant spirals, their chambered shells regulating buoyancy as they hunted smaller prey. Belemnites, streamlined and swift, navigated the midwater column with internal guards that would one day fossilize in stone. Schools of fish wove between coral branches, while crustaceans scuttled across reef surfaces in constant search of shelter. Above and beyond the platforms, larger silhouettes moved with measured authority. Ichthyosaurs, shaped by convergent evolution into forms reminiscent of modern dolphins, coursed through deeper channels in pursuit of prey. Plesiosaurs, with elongated necks and powerful flippers, patrolled the margins between reef and open sea, their presence linking shallow ecosystems to broader marine realms. Tropical seas, such as this, fostered biodiversity because temperature gradients remained gentle, reducing seasonal stress and permitting long evolutionary continuity. Warm water enhanced metabolic rates, accelerating growth and reproduction, while the structural complexity of reefs generated countless microhabitats. Crevices, overhangs, and sheltered lagoons offered protection and opportunity in equal measure, encouraging specialization and interdependence. Energy flowed efficiently from sunlight to plankton to predators, sustaining food webs that reached from the smallest algae to apex marine reptiles. As carbonate sediments thickened, they gradually lithified into limestone, preserving within their crystalline matrix the architecture of ancient reefs. Each reef cycle added new layers to the platform, raising the seafloor incrementally and extending habitats laterally across the basin. Over immense spans of time, these accumulations achieved extraordinary thickness, forming deposits that would endure long after the sea itself had changed. In this luminous equatorial expanse, the Tethys supported a world of reefs whose quiet construction shaped not only coastal landscapes, but the geological record that would remember them long after the waters had shifted elsewhere. Across the surface of the Tethys, heat did not remain still. It traveled. Sunlight absorbed in equatorial waters was carried outward through broad, persistent currents, weaving a thermal pathway between continents that were still arranging themselves. These currents did more than move water. They redistributed energy. softening contrasts between regions and shaping the atmosphere above in ways that would define the character of the Mesozoic world. During the Jurassic and Cretaceous periods, global temperatures remained elevated under a greenhouse climate sustained by higher concentrations of carbon dioxide and vigorous volcanic outgassing along spreading centers. Polar ice was limited or absent for long intervals, allowing sea levels to remain high and coastlines to extend deep into continental interiors. Without expansive ice sheets to reflect sunlight, more solar radiation was retained, reinforcing a cycle of warmth that extended from tropics toward higher latitudes. The Tethys, positioned across equatorial zones, functioned as a reservoir of thermal energy, absorbing, storing, and gradually releasing heat into surrounding circulation systems. Warm surface waters rising from the basin influenced atmospheric pressure gradients, guiding prevailing winds along predictable seasonal paths. As continents drifted and mountain belts adjusted elevation, these winds encountered shifting barriers and open corridors, giving rise to early monsoonal patterns over adjacent landmasses. Moist air, drawn inland from the Tethys, condensed over coastal plains and uplands, delivering rainfall that sustained river systems and wetlands far from the open sea. In turn, runoff returned minerals and nutrients to marginal shelves, subtly linking climatic processes with marine productivity. The geometry of the basin also affected deep ocean circulation. Differences in temperature and salinity created density gradients that encouraged slow overturning motions, connecting surface warmth to deeper layers and distributing dissolved gases across wide expanses. Through these exchanges, the Tethys became integrated with other global oceans, influencing how heat moved between hemispheres. The relative absence of strong polar cooling reduced extreme seasonal swings, allowing ecosystems across many latitudes to persist with fewer abrupt climatic disruptions than those characteristic of later eras. Storm tracks trace the boundaries between warm ocean air and continental interiors, and tropical cyclones likely formed over expansive warm waters, their energy drawn directly from the sea's stored heat. Over millions of years, this steady interplay between ocean and atmosphere established a climatic equilibrium that favored lush vegetation and extensive shallow seas. The Tethys did not operate in isolation but as a central artery within a planetary system, modulating temperature contrasts and guiding moisture across emerging landscapes. In this prolonged warmth, Earth's surface responded with gradual adjustments rather than sudden shocks. The climate engine of the Mesozoic was not a singular force but a network of interactions, with the Tethys at its luminous core, circulating heat through water and air alike, shaping patterns that would endure until tectonic rearrangements slowly altered the pathways once more. Along the margins where land inclined gently toward the Tethys, coastlines unfolded in long, irregular curves across regions that would one day become North Africa and southern Europe. These shores were not fixed lines but living boundaries, advancing and retreating with subtle fluctuations in sea level and sediment supply. River systems carried silt and dissolved minerals from inland highlands, releasing them into deltas that fanned outward into the warm shallows. Over time, layers of sand and mud settled into broad coastal plains, shaping estuaries where freshwater mingled with salt in slow, shifting gradients. Vegetation colonized these transitional zones, forming dense wetlands reminiscent of modern mangrove environments, though composed of ancient plant lineages adapted to brackish conditions. Root networks stabilized the sediment, trapping additional particles and building low platforms that rose incrementally above tidal reach. Within sheltered lagoons, behind barrier systems, Calm waters fostered nurseries for fish and invertebrates, their life cycles synchronized with the rhythms of tides and seasonal rainfall. These protected basins served as ecological bridges between open sea and terrestrial habitats, concentrating nutrients and sustaining diverse communities along narrow corridors. On adjacent floodplains and coastal uplands, early dinosaurs moved through landscapes shaped by proximity to the sea. Some species foraged along vegetated margins, while others traversed sandy flats left exposed during low tides. The presence of abundant fish and invertebrates in shallow shelves attracted predators to the water's edge, linking marine productivity to terrestrial food webs. Fossil trackways preserved in tidal sediments reveal patterns of movement across mud that once lay soft beneath reptilian feet, later hardened and buried under successive deposits. Shallow continental shelves extended outward from these coasts, illuminated and rich with plankton carried by gentle currents. Fish thrived in these nutrient-laden waters, their populations supported by upwelling and the steady delivery of organic matter from both land and sea. Tidal forces sculpted channels and sandbars, redistributing sediment with each cycle and creating microhabitats that shifted subtly over years and centuries. Storm surges occasionally reworked entire stretches of shoreline, depositing coarse layers that recorded episodic energy within an otherwise gradual system. Across millions of years, the geometry of these coastlines changed as tectonic motion altered basin shape and regional elevation. Subsidence deepened some margins, inviting further marine transgression, while uplift elsewhere narrowed shelves and exposed former seabeds to erosion. The boundary between land and ocean migrated slowly across the map, carrying ecosystems with it and preserving their traces in stacked sequences of sandstone, shale, and limestone. In this interplay between water, sediment, and living communities, the shores of the Tethys remained dynamic yet continuous, shaping both the creatures that inhabited them and the geological record that would one day reveal their existence. Far below the sunlit shelves and shifting coasts, the floor of the Tethys unfolded in darkness, shaped not by waves or tides, but by the steady ascent of heat from Earth's interior. A submerged ridge traced the basin's axis, rising in a broad, sinuous chain that marked the boundary between diverging plates. Along its crest, fissures opened into glowing chambers where magma gathered before spilling upward, cooling abruptly against seawater and solidifying into fresh basalt. Each pulse added a narrow strip of new crust, pushing older rock outward in a patient, symmetrical expansion that widened the ocean over spans beyond ordinary imagination. This newly formed oceanic crust differed profoundly from the continental masses it separated. It was thinner, denser, composed largely of basalt and gabbro rather than the buoyant granitic assemblages that anchored continents. Beneath a veneer of sediment, its thickness remained modest, while continental crust extended far deeper, layered and complex, from ancient cycles of collision and metamorphism. The contrast governed their fate. Continental blocks resisted descent, while oceanic lithosphere, once cooled and thickened, would eventually bend and sink back into the mantle. Near the ridge, hydrothermal systems flourished, where seawater percolated through fractured rock, descending, heating, and rising again enriched with dissolved minerals. At vent fields, dark plumes issued from chimney structures built of sulfide deposits, their mineral-rich effluent precipitating upon contact with cold seawater. Around these vents, life organized itself without reliance on sunlight. Microbial communities drew energy from chemical gradients, supporting invertebrates adapted to warmth and toxicity, their bodies sustained by chemosynthetic symbiosis. In this dim environment, the Tethys harbored ecosystems fundamentally different from those of its illuminated margins, yet equally integrated into the ocean's fabric. As seafloor spreading continued, magnetic minerals within cooling basalt aligned with the orientation of Earth's magnetic field at the moment of solidification. Over geological intervals, reversals in that field imprinted alternating bands of normal and reversed polarity across the expanding crust. These magnetic stripes, arranged in mirror symmetry on either side of the ridge, preserved a silent chronicle of formation rates and directional change, encoding the tempo of tectonic motion within stone. Farther from the ridge, the crust cooled, thickened, and accumulated sediment shed from distant continents and drifting plankton. Gradually, its density increased, preparing it for eventual descent along subduction zones at the basin's margins. There, the oceanic plate would curve downward, carrying with it basalt, sediment, and traces of the deep biosphere into the mantle's hotter domain. This recycling unfolded without spectacle, a continuous exchange between surface and interior that balanced creation with consumption. Through these processes, the ocean floor of the Tethys remained in constant renewal, its dark expanse both birthplace and pathway within the enduring cycle of Earth's tectonic life. Movement on a planetary scale rarely announces itself. It proceeds in increments so small that no creature living upon the surface could sense it. Yet, across spans of deep time, those increments reshape entire hemispheres. While the Tethys matured and circulated warmth through the ancient world, the continents bordering it continued their gradual migration, guided by forces far below their foundations. From the southern supercontinent of Gondwana, a fragment began to detach, its margins defined by rifts that widened imperceptibly from year to year. This fragment was the landmass that would become India, once fused to Africa, Antarctica, and Australia. It loosened along zones of thinning crust and entered a northward journey across the Tethyan waters. The speed of this passage measured only centimeters per year, a pace comparable to the growth of a fingernail, yet sustained over tens of millions of years. It carried an entire continent across vast latitudinal distances. As it moved, new oceanic crust formed in its wake, recording separation within the deep floor left behind. Africa, too, drifted steadily northward, narrowing the space between itself and Eurasia. Its leading edge approached subduction zones that had begun to consume older segments of oceanic lithosphere. Meanwhile, Eurasia adjusted in response, shifting subtly east and west along complex boundaries that redistributed stress across mountain belts and inland basins. None of these motions were abrupt. They unfolded through the slow glide of rigid plates over the more ductile asthenosphere, lubricated by heat and maintained by convection currents circulating through the mantle. Measured in isolation, a few centimeters per year appear insignificant. Yet when multiplied by spans reaching into tens of millions of years, such displacement transforms geography. Coastlines advance into new climatic zones, marine corridors constrict or widen, and the relative positions of land and sea alter patterns of circulation established long before. The Tethys, once expansive, experienced gradual reconfiguration as its surrounding margins converged and diverged in different sectors. Its width in some regions increased temporarily, even as in others the first hints of compression began to emerge. Ocean basins in geological time are not permanent fixtures but phases within a larger tectonic cycle. They open when continents rift apart and close when those same masses drift back together under the persistence of plate motion. The creation of seafloor along spreading ridges balances its destruction at subduction zones, maintaining a dynamic equilibrium that ensures renewal rather than stasis. As India pressed northward and Africa advanced toward Eurasia, the Tethys entered a new chapter shaped by convergence as much as divergence. All of this occurred without spectacle at the human scale, guided by forces measured not in moments but in epochs. Through steady motion, continents carried with them climates, ecosystems, and sedimentary histories, altering the architecture of the planet in increments so small that only the accumulated record within stone reveals the magnitude of their journey. At the margins of the basin, the geometry of motion began to alter. What had once been dominated by separation now carried the first quiet signals of return. Along certain edges of the Tethys, the oceanic plate, cooled and thickened during its long outward journey from the ridge, approached continental boundaries and began to bend. The descent was subtle at first, a downward flexure where dense lithosphere yielded to gravity and slipped beneath lighter crust. In these curving zones, subduction established itself not as an abrupt event, but as a gradual reorientation of force. As the oceanic slab angled into the mantle, it carried with it sediments accumulated over millions of years, along with basalt formed at distant spreading centers. Increasing pressure and temperature transformed minerals within the descending plate, releasing water that rose into the overlying mantle wedge. This infusion lowered melting temperatures, generating buoyant magmas that ascended toward the surface. Over time, volcanic arcs emerged above these subduction zones, tracing sweeping lines parallel to the continental margins. Islands and peninsulas grew from repeated eruptions, their lavas recording the chemistry of deep interactions between crust and mantle. Beneath these arcs, earthquakes marked the frictional boundaries between converging plates. The descending slab fractured incrementally as it adjusted to new stresses, producing tremors that migrated downward along the inclined plane of subduction. Though imperceptible, at human scales of time, these seismic patterns outlined the geometry of convergence with remarkable precision. Each tremor reflected accumulated strain released along locked segments of the boundary, a mechanical response to persistent compression. Where subduction advanced, the width of the Tethys began to diminish. Oceanic crust that had once expanded confidently from mid-ocean ridges was now consumed at its edges, recycling into the mantle's deeper circulation. The balance between creation and destruction shifted regionally, favoring closure over growth. Sediments scraped from the descending plate accumulated in wedge-shaped prisms along the trench, thickening and deforming under pressure. Folds developed within these accreted layers, subtle at first, then increasingly pronounced as convergence continued. Compression transmitted itself inland, reactivating older faults and elevating foreland basins. The once expansive marine corridor sensed constraint along its periphery, even while open water still stretched broadly across its center. The transformation unfolded unevenly, with some sectors remaining in extension while others entered contraction. Yet the overall trajectory had changed. The tectonic rhythm that had given birth to the basin now initiated its gradual narrowing. Through these processes, the Tethys entered a new phase defined by convergence rather than divergence. Subduction zones etched themselves into its margins, volcanic arcs rose in graceful chains, and seismic energy pulsed intermittently through the crust. The ocean had not vanished, nor had its warmth faded, but the quiet mechanics of compression signaled that its broad expanse would not remain indefinitely unchallenged within the ceaseless cycle of plate motion. The map of the Tethys did not change in a single gesture, but in gradual adjustments that redefined its edges and internal pathways. Regions that had once opened freely toward distant waters began to constrict as converging plates consumed the intervening crust. The breadth of the basin lessened unevenly, narrowing first along active margins where subduction persisted, while more central expanses retained their open character for a time. What had been a vast marine corridor slowly acquired boundaries shaped by rising land and descending lithosphere. Chains of volcanic islands emerged above the zones of descent, their peaks aligned in graceful arcs that paralleled the trenches below. Each island represented the surface expression of magma generated deep within the mantle wedge, rising through fractured crust and accumulating in successive eruptions. Ash layers settled across nearby waters, and lava flows built stratified cones that withstood waves and weather. Over long intervals, some arcs coalesced into larger landmasses, creating partial barriers within the ocean and altering patterns of current and sediment transport. Adjacent to these arcs, deep trenches marked the sites where oceanic crust bent downward into the mantle. Their profiles carved elongated depressions along the basin's margins, shadowed and steep, accumulating thick sequences of scraped sediment. Within these trenches, water descended into darkness, while tectonic forces operated beneath, drawing older seafloor into regions of greater pressure and temperature. The combined effect of trench formation and arc uplift reduced the effective width of navigable marine passages, transforming what had been expansive routes into more segmented networks. As connections between sectors of the Tethys grew restricted, circulation patterns adjusted. Currents that once flowed unimpeded encountered new obstacles, diverting around islands or narrowing through straits formed between arc systems and continental edges. Changes in water exchange influenced temperature gradients and salinity distribution, subtly reshaping ecological conditions across different regions of the basin. Some marine organisms adapted to these altered pathways, thriving in newly isolated environments where gene flow became limited and evolutionary divergence accelerated. Other species, specialized for open and continuous habitats, faced reduced ranges as corridors contracted. Biodiversity did not collapse, but redistributed itself, reflecting the dynamic geography beneath. Reef systems responded to shifting currents and sediment loads, expanding in sheltered areas while declining where turbidity increased. Pelagic species adjusted migratory routes in accordance with emerging landforms and changing nutrient patterns. Through these biological responses, the narrowing sea left its imprint not only in stone but within the evolutionary trajectories of its inhabitants. The Tethys, once defined by breadth and connectivity, entered a phase characterized by segmentation and constraint. Volcanic arcs stood as surface markers of deeper convergence. Trenches recorded the descent of crust, and circulation reorganized around new barriers. The transformation unfolded over immense spans, without abrupt disappearance, yet with a clear directional movement toward reduction. In this steady contraction, the ocean's identity began to shift from expansive gateway to partitioned remnant within the larger choreography of tectonic change. Long after the first arcs had risen and the basin had begun its slow contraction, mammals moved along low coastal plains bordering the remaining reaches of the Tethys. These were small, hoofed creatures, adapted to life on land, yet drawn toward estuaries and sheltered inlets where rivers met the sea. In sediments that would one day surface in regions now called Pakistan and North Africa, Their bones would be preserved, recording a transformation that unfolded along the margins of this changing ocean. Among these early forms were animals that still bore the proportions of terrestrial mammals, with sturdy limbs capable of supporting weight on land. Yet their skulls reveal subtle shifts, the placement of ear bones suggesting adaptation to hearing in water, the elongation of jaws suited to grasping fish. Over successive generations, selection favored individuals more comfortable in shallow marine environments. Limbs gradually reshaped into paddles, hind legs reduced, and vertebral columns elongated to permit powerful undulating motion. The nostrils migrated backward along the skull, an incremental relocation that would ultimately position them atop the head as a blowhole. The shallow epicontinental seas that fringed the Tethys offered ideal conditions for this transition. Warm, relatively protected waters supported abundant fish and invertebrates, providing reliable food sources within reach of animals not yet fully committed to life offshore. Broad shelves allowed gradual immersion rather than abrupt descent into deep ocean, enabling mammals to forage in waist-deep water before venturing farther from land. In lagoons and tidal channels, they could retreat to rest or give birth, balancing terrestrial ancestry with aquatic opportunity. Fossil assemblages from these regions preserve a sequence of forms that trace this evolutionary pathway with remarkable clarity. Early genera exhibit functional legs alongside aquatic adaptations, while later species display increasingly streamlined bodies and diminished pelvic connections. Isotopic signatures in their teeth indicate feeding within marine settings, confirming that dietary shifts accompanied anatomical change. The record does not suggest sudden transformation, but a continuum of modification shaped by ecological advantage and environmental stability. As these proto whales expanded their range, they became part of the marine ecosystems that had long flourished within the Tethys. Their emergence illustrates how tectonic and climatic processes influence biological history. Without extensive shallow seas positioned in warm latitudes, the opportunity for such a transition might have been constrained. The ocean provided both habitat and selective pressure, encouraging experimentation in locomotion, respiration, and sensory perception. Through this gradual adaptation, mammals entered a realm once dominated by reptiles and fishes, eventually giving rise to lineages that would inhabit oceans across the globe. The Tethys, even in its narrowing phase, served as a cradle for this transformation, embedding within its sedimentary layers the evidence of a profound shift in mammalian destiny, a reminder that the boundaries between land and sea can become pathways rather than limits. Toward the closing chapters of the Cretaceous, the equilibrium that had long sustained tropical marine systems began to waver. Sea levels, once persistently elevated, fluctuated as tectonic adjustments altered the volume of ocean basins and the configuration of spreading ridges. Subtle regression exposed portions of continental shelves that had remained submerged for millions of years, narrowing habitats that reef communities depended upon. In other intervals, renewed transgression briefly restored shallow platforms, yet the rhythm had grown less stable than in earlier epochs. At the same time, the chemistry of seawater responded to both tectonic and atmospheric change. As subduction intensified along converging margins, volcanic activity released gases that influenced carbon cycles, while weathering of newly uplifted terrains altered the balance of dissolved ions delivered to the sea. Variations in carbon dioxide concentration affected global temperatures and ocean acidity, influencing the saturation state of calcium carbonate. Reef building organisms, reliant on favorable chemical conditions to construct their skeletons, experienced periods of stress when saturation declined or temperatures shifted beyond optimal ranges. Then, near the boundary that marked the end of the Cretaceous, a sudden external force interrupted these gradual transformations. An asteroid impact injected dust and aerosols into the atmosphere, dimming sunlight and disrupting photosynthesis across marine and terrestrial ecosystems. In the oceans, plankton communities that formed the base of food webs suffered abrupt decline. Without consistent primary productivity, energy transfer through trophic levels faltered, and many species dependent on stable marine conditions disappeared within a comparatively brief geological interval. Coral reef systems, already navigating fluctuating sea levels and chemical variability, faced compounded stress. Some reef complexes collapsed as symbiotic relationships between corals and photosynthetic partners broke down under reduced light and altered temperature regimes. Sedimentation patterns shifted as coastal vegetation declined and erosion intensified in destabilized landscapes, delivering increased terrestrial material into adjacent seas. Layers of fine debris accumulated in places where carbonate production once dominated, recording a temporary suppression of reef growth. Yet the impact did not erase all marine life. Certain lineages persisted in refugia, adapting to cooler and darker conditions before gradual climatic recovery restored more stable environments. Over time, new reef assemblages emerged, though often with altered species composition and reduced structural complexity compared to earlier flourishing systems. The geological record preserves this transition as a distinct boundary, marked by changes in fossil assemblages and sediment character. Within these shifts, the Tethys bore witness to both continuity and interruption. Tectonic motion continued its steady course even as ecological networks reorganized. The interplay between slow internal processes and sudden external disturbance shaped a marine landscape that would not fully return to its former state, signaling that even long-enduring tropical seas remain subject to forces capable of profound transformation. Across the broad expanse that remained of the Tethys, a solitary continent advanced with unusual haste. Detached from Gondwana and freed into open water, the Indian plate traveled northward at a velocity that surpassed most modern plate motions. Measured in centimeters per year, its pace would have seemed trivial within a single lifetime. Yet, sustained across tens of millions of years, it carried an entire landmass from southern latitudes into the heart of the ancient ocean. The journey unfolded without spectacle, guided by mantle convection and the geometry of surrounding plates. As India progressed, the oceanic crust before it diminished. Subduction zones along the southern margin of Eurasia consumed the intervening seafloor, drawing dense lithosphere downward into the mantle. Each segment of descending crust represented a portion of the Tethys erased through compression. Sediments scraped from the subducting plate accumulated along the edge of Eurasia, thickening into deforming wedges that recorded the approach of the advancing continent. The basin narrowed not only through arc formation, but through the persistent forward motion of this migrating block. Magnetic minerals locked within basaltic crust preserved a detailed account of India's voyage. As seafloor spreading continued behind the drifting plate, alternating bands of normal and reverse polarity formed in mirror symmetry along ridges in the Indian Ocean. By matching these magnetic stripes to known reversals in Earth's magnetic field, geologists reconstructed the speed and direction of movement with remarkable precision. The pattern revealed an interval of accelerated drift, a rapid crossing of latitudes that positioned India directly in the path of Eurasia. During this transit, marine corridors ahead of the plate contracted steadily. The once extensive Tethyan waters became segmented by arcs and trenches, and the distance between continental margins shortened with each passing million years. Oceanic crust that had formed during earlier phases of expansion now met its end in subduction zones, sinking into the mantle as India advanced. The balance between creation at distant ridges and destruction along convergent boundaries tipped decisively toward closure in this sector of the basin. Within the narrowing sea, currents adjusted to the shifting geometry, and sedimentation patterns altered as shorelines drew closer together. The impending convergence between India and Eurasia began to influence regional stress fields, subtly reorienting faults and initiating the earliest stages of uplift along distant margins. Yet, for long intervals, open water still lay between the two continents, even as its width diminished. India's northward drift illustrates how plate motion, though measured in small annual increments, can reshape global geography when sustained over deep time. The shrinking Tethys ahead signaled that collision was no longer a distant possibility, but an approaching inevitability. Embedded within the persistent mechanics of tectonic movement and recorded quietly in magnetic signatures across the ocean floor. Pressure accumulated where motion could no longer be accommodated by simple descent. The remaining stretches of Tethyan oceanic crust, once broad and continuously renewed, were drawn steadily into subduction zones that had migrated closer to one another. As India approached Eurasia and Africa advanced from the southwest, the basin's surviving seafloor narrowed into confined corridors bordered by trenches of increasing depth. These trenches marked the final pathways through which oceanic lithosphere descended, their profiles steep and shadowed, recording the relentless pull of gravity upon dense crust. With less distance separating converging plates, strain intensified along their boundaries. Earthquakes became more frequent and penetrated deeper into the mantle as slabs adjusted to sharper angles of descent. Seismic energy traced inclined planes beneath the surface, outlining the geometry of subduction in patterns later preserved within mineral transformations. Each tremor signaled friction released along locked interfaces where opposing forces met, a mechanical dialogue between advancing continents and resisting seafloor. Volcanic arcs that had once stood offshore began to approach continental margins. Islands formed through earlier episodes of magmatism collided with the edges of larger landmasses, welding themselves onto continental crust. Their volcanic cores were compressed, fractured, and in places uplifted as fragments of the arc were incorporated into growing mountain belts. Marine sediments that had accumulated along their flanks were caught between converging plates, folded and thrust upward in complex stacks. Along the margins of Eurasia and adjacent regions, thick sequences of limestone, shale, and sandstone were scraped from the descending plate and piled into accretionary prisms. These sediments, originally deposited in calm marine settings, now experienced deformation under immense horizontal stress. Layers bent into tight folds, faults propagated through once flat strata, and blocks were transported kilometers from their original positions. The former floor of the Tethys, composed of both volcanic rock and layered sediment, became an active participant in continental construction. Deep within subduction zones, the last fragments of oceanic crust were metamorphosed under pressure, releasing fluids that fueled additional magmatism in overlying regions. Yet the overall balance shifted decisively toward closure. Creation at distant ridges could no longer offset destruction along converging fronts. The ocean that had once connected distant realms found its remaining space compressed between approaching continental masses. Through this final compression, the Tethys transitioned from an expansive marine basin to a series of diminishing pockets bordered by rising terrain. Trenches deepened as conduits of descent, earthquakes recorded the tightening grip of convergence, and sediments accumulated in thickened wedges that foreshadowed uplift. The ocean's identity changed not through sudden disappearance, but through steady consumption, as tectonic forces gathered the remnants of its floor into the growing architecture of colliding continents. When the last significant stretches of intervening seafloor had been drawn downward, two buoyant masses finally met. The leading edge of India pressed into the southern margin of Eurasia, and for the first time since their separation from older supercontinents, continental crust collided directly with continental crust. Unlike oceanic lithosphere, which readily bends and sinks because of its greater density, continental crust resists subduction. Composed of lighter, silica-rich rocks and thickened by earlier tectonic histories, it refuses to descend easily into the mantle. Instead, it deforms. At the moment of contact, motion did not cease. The Indian plate continued to advance, but without dense oceanic crust ahead to consume, the energy of convergence was transferred into compression. Layers of rock crumpled and stacked, thrust faults carried slabs of crust over one another, and the combined thickness of the colliding margins began to increase. The crust, once extended across distant latitudes, shortened horizontally and expanded vertically. This process unfolded gradually, yet its cumulative effect was profound. Marine sediments that had accumulated quietly on the floor of the Tethys were caught between the approaching continents. Limestones formed from ancient reefs, shales deposited in deeper waters, and sandstones laid down along shifting shores were squeezed and uplifted. Some layers folded into sweeping arcs, others fractured and rode upward along thrust plains. What had once rested beneath warm seas now rose into air, carried skyward by the inexorable mechanics of plate convergence. As crust thickened, its deeper portions heated and partially melted, generating granitic intrusions that reinforced the growing mountain belt. The buoyancy of the thickened crust contributed to further uplift, a phenomenon often described as isostatic adjustment, in which thicker crust floats higher upon the denser mantle beneath. Erosion began almost as soon as elevation increased, rivers carving into new relief and transporting sediment away from rising peaks. Yet even as erosion wore down summits, ongoing convergence replenished their height, maintaining a dynamic balance between uplift and removal. Through millions of years of continued compression, the early Himalayan ranges took form along the suture, where India and Eurasia joined. The mountains did not appear in a single dramatic gesture, but emerged through incremental stacking and thickening, each episode of thrusting adding to their stature. Beneath them, fragments of former oceanic crust and marine sediment were locked within the developing origin, preserving within their minerals the memory of a vanished sea. The collision transformed not only regional topography, but atmospheric circulation and hydrology across adjacent lands. Yet at its core, the process remained a simple consequence of buoyant crust meeting buoyant crust. Continents could not sink into one another, so they rose, and in rising they converted the last substantial breadth of the Tethys into stone that would stand above the clouds, high above present coastlines. Where air thins and snow gathers along serrated ridges, stone preserves the memory of water. Within the uplifted layers of the Himalayas lie shells once carried by gentle currents, their spiral forms pressed into rock that now stands among the highest elevations on Earth. These fossils, embedded within limestone and shale, testify to a time when this terrain rested beneath a tropical sea. Their delicate structures survived burial, compression, and ascent, emerging intact within strata that no longer know the touch of waves. Limestone dominates many of these elevated outcrops, its composition derived from accumulated carbonate sediments that formed on ancient seabeds. Microscopic skeletal fragments, coral debris, and shells compacted into thick sequences long before tectonic forces raised them skyward. At extreme altitudes, blocks of this pale rock reveal bedding planes that once lay horizontal in quiet marine settings. Now tilted and folded, they chart the deformation that accompanied continental collision, preserving the original textures of deposition even as their orientation changed dramatically. Interspersed among these sedimentary layers are darker, denser rocks known as ophiolites, fragments of former oceanic crust thrust onto land during convergence. These sequences typically include basalt, gabbro, and mantle-derived peridotite, arranged in patterns that mirror the structure of seafloor created at mid-ocean ridges. Their presence within mountain belts offers direct evidence that pieces of the Tethys floor were not entirely consumed by subduction, but instead emplaced atop continental margins during collision. In places, pillow basalts display rounded forms shaped by rapid cooling in seawater, unmistakable signatures of submarine origin. Field geologists trace these materials across remote valleys and ridgelines, mapping contacts between sedimentary units and igneous intrusions. Radiometric dating constrains the ages of volcanic components, while fossil assemblages within adjacent limestones provide biostratigraphic markers that align sequences across distant regions. Paleomagnetic measurements record the latitudinal position at which rocks formed, allowing reconstruction of plate movement through time. Together, these methods assemble a coherent narrative from scattered outcrops, transforming isolated exposures into chapters of a larger tectonic history. The reconstruction of ancient oceans relies upon this integration of evidence, each dataset reinforcing the others. Structural analysis reveals the direction of compressive forces. Mineral assemblages indicate pressure and temperature conditions experienced during uplift. Sedimentary facies reflect former depths and environments. Through patient synthesis, geologists restore the geometry of vanished basins, outlining coastlines and ridges long erased from the surface. In the Himalayas, seafloor resides in the sky, not as metaphor, but as material reality. Fossils, limestone, and ophiolitic fragments stand as tangible remnants of the Tethys, preserved within the architecture of rising mountains. Their presence affirms that oceans, though immense, can be folded into stone, their histories encoded in layers that await careful reading among the heights. Where once a continuous tropical corridor had stretched between continents, only segmented waters remained. As convergence progressed and mountain belts rose along former ocean margins, the broad Tethyan domain fragmented into smaller basins, isolated by uplift and shifting plate boundaries. These remnant seas occupied depressions left between colliding landmasses, preserving portions of the ancient marine system even as the greater expanse disappeared. Among these survivors were the Neotethys and the Paratethys, basins that retained marine connections, while surrounding regions transformed into highlands and interior plains. The Neotethys persisted along the southern margin of Eurasia for a time, bordered by volcanic arcs and evolving continental edges. The Paratethys extended across parts of what are now Central and Eastern Europe, forming a complex inland sea that fluctuated in extent as tectonic adjustments modified its gateways. Each basin reflected a different stage in the retreat of the original ocean, their waters constrained by rising terrain and narrowing straits. As Africa continued its gradual northward motion, the configuration of these remnants shifted further. The basin that would become the Mediterranean formed within a zone of interaction between the African and Eurasian plates. Subduction and back arc extension created space even as compression elsewhere closed passages. The resulting sea inherited both the lineage and the instability of its Tethyan predecessor, occupying a region shaped by opposing tectonic forces. At intervals, connections between the Mediterranean basin and the open Atlantic were restricted or severed. During one dramatic episode, known as the Messinian Salinity Crisis, tectonic uplift and changing sea level isolated the basin sufficiently to limit inflow from the global ocean. Evaporation exceeded replenishment, leading to substantial drawdown of water levels and the precipitation of thick evaporite deposits across the basin floor. Salt layers accumulated in sequences that later became buried beneath younger sediments, preserving evidence of extreme chemical concentration within a once marine environment. Despite such episodes of isolation, the Mediterranean endured because tectonic processes also reopened pathways. Subsidence and renewed connection to the Atlantic allowed waters to return, refilling the basin and restoring marine conditions. Its continued existence reflects a balance between closure and extension, between uplift and subsidence, that has characterized the region since the fragmentation of the Tethys. Today's Mediterranean is therefore not an entirely new creation, but a descendant, a remnant shaped by the same tectonic currents that governed its ancestor. The Neotethys and Paratethys have largely vanished or transformed into inland seas and basins, yet their histories remain inscribed in sedimentary records across Europe and Western Asia. Through these surviving waters, the legacy of the Tethys persists, diminished in scale yet enduring as a testament to the complex pathways by which oceans fade, fragment, and occasionally return. Across southern Europe, the imprint of the vanished sea appears not in open water, but in stone that rises in long, sweeping arcs. The Alps stand as one of the most visible expressions of this transformation, their peaks composed in large part of sediments once deposited along the floor and margins of the Tethys. Limestone, marl, and sandstone that accumulated in shallow shelves and deeper basins were drawn into converging zones as Africa and Eurasia approached, compressed and uplifted into the mountain chain that now spans the continent. As convergence intensified, layers of marine sediment did not simply rise intact. They folded under horizontal pressure, forming anticlines and synclines that ripple across the landscape in repeating patterns. These folds record directional stress applied over immense spans, their geometry revealing the forces that shortened and thickened the crust. In some sectors, thrust faults transported entire packages of sedimentary rock tens of kilometers over underlying units, stacking strata in imbricated sheets that increased elevation while preserving traces of their marine origin. The Carpathians, curving across Central and Eastern Europe, reflect a similar history. Though differing in structural detail, they too incorporate materials once laid down beneath Tethyan waters. Subduction and later collision rearranged these sediments into belts that arc around former basins, creating mountain systems whose alignment traces the contours of long vanished shorelines. In places, ophiolitic fragments and deep marine deposits accompany these sequences, marking zones where oceanic crust and pelagic sediments were caught within the advancing folds. Throughout these ranges, the evidence of ancient seabeds is preserved in both fossil content and lithology. Ammonites, bivalves, and microscopic foraminifera remain embedded within rock faces exposed by erosion. Cross-bedding within sandstones indicates currents that once moved across submerged platforms, while fine laminations in shales suggest quiet deposition in deeper settings. The orientation of these layers, often steeply inclined or even overturned, contrasts with their original horizontal arrangement, underscoring the magnitude of deformation that accompanied mountain building. Metamorphism affected some units as they were buried and heated during compression, altering mineral assemblages while retaining sedimentary textures. Elsewhere, less intense conditions allowed fossils and bedding to remain clearly visible, offering accessible windows into the marine environments from which they derived. Geologists map these sequences across vast distances, correlating formations between the Alps, the Carpathians, and adjacent ranges to reconstruct the continuity of the former basin. In these European mountains, the Tethys persists as structure rather than water. Each fold and thrust sheet encodes a chapter of its closure. Each limestone cliff and fossil-bearing layer affirms its prior existence. The ranges that define much of Europe's topography are thus not isolated features, but elevated remnants of a shared marine past, shaped by convergence and preserved in the architecture of stone that once lay beneath a tropical sea. Wind now moves across dunes that stretch toward the horizon, lifting fine grains into shifting veils of gold and amber. Beneath this vast expanse of arid terrain, layers of stone preserve a quieter history, one shaped not by desiccation but by immersion. In portions of North Africa, rock sequences reveal intervals when shallow marine waters extended far inland, covering regions that today lie within the Sahara. Limestone beds and fossil-rich strata attest to episodes during which warm seas lapped against low-lying margins, depositing shells and carbonate mud across broad platforms. Marine fossils appear in outcrops scattered across the desert, embedded within sedimentary layers that once accumulated on submerged shelves. Ammonites, bivalves, and microscopic organisms remain preserved in relief against pale rock faces, their forms contrasting with the surrounding sand. These fossils confirm that parts of the Sahara were not always dry, but participated in the wider Tethyan system during phases of high sea level and favorable tectonic configuration. Sedimentary structures, such as ripple marks and cross-bedding, further record currents that moved through shallow waters, sculpting seabeds that would later be lifted and exposed. The transformation from tropical sea to arid desert unfolded gradually as tectonic rearrangements altered regional geography. As Africa advanced northward and the Tethys narrowed, marine incursions retreated from interior basins. Uplift associated with distant collisions, modified drainage patterns, and influenced atmospheric circulation. Over millions of years, shifts in global climate reduced precipitation across northern Africa, encouraging the expansion of dry conditions. The interplay between plate motion and atmospheric dynamics redirected moisture pathways, diminishing the influence of maritime air masses that once penetrated inland. Sedimentary records within the Sahara capture this transition in layered sequences. Marine limestones give way to continental sandstones and evaporite deposits, reflecting the replacement of open water by restricted basins and eventually by terrestrial environments. Fossil assemblages change accordingly, marine species replaced by organisms adapted to freshwater or arid settings. In some intervals, brief returns of wetter conditions left traces of lakes and river systems. Yet, the long-term trend favored increasing aridity as continental positions stabilized and global climate oscillated through cooler phases. The desert visible today represents only the latest chapter in this evolving landscape. Its dunes rest upon rock shaped by marine deposition and later sculpted by wind. Beneath the surface, aquifers occupy porous layers that once formed beneath shallow seas, storing groundwater within sediments laid down in distant epochs. The Sahara's present dryness does not erase its marine past, but overlays it, preserving within stone the memory of a time when tropical waters extended across what is now a realm of sand. Through these changes, the legacy of the Tethys persists even in absence. Fossils and strata across North Africa bear witness to the shifting boundary between sea and land, demonstrating that environments perceived as permanent are stages within longer cycles of tectonic and climatic transformation. As the Tethys diminished and its passages narrowed into fragmented basins, a different ocean was widening across the globe. Along the line where continents had once fit together within Pangea, seafloor spreading continued with steady persistence, and the Atlantic expanded between the separating margins of the Americas, Africa, and Europe. With each increment of newly formed crust, the geometry of global circulation shifted, redistributing the pathways through which heat moved between hemispheres. The Atlantic did not simply add surface area to the planet's oceans, it altered their connectivity. As its basin broadened, water exchange between northern and southern latitudes intensified along new routes. Warm equatorial currents began to arc northward along the eastern coasts of the Americas, while cooler waters flowed southward along opposing margins. These reorganized patterns gradually replaced the equatorial corridor, once dominated by the Tethys, transferring the primary role of heat distribution to the expanding Atlantic system. Changes in heat transport influenced atmospheric circulation on a planetary scale. Regions that had once relied upon the Tethys for moderating temperature experienced new climatic regimes shaped by Atlantic currents. The redistribution of warmth affected evaporation, precipitation, and the positioning of storm tracks. Over extended intervals, such adjustments contributed to shifts in global temperature gradients, setting the stage for cooler phases that contrasted with earlier greenhouse conditions. As continents approached more modern configurations, the isolation of polar regions increased. The development of circumpolar currents around Antarctica, and later the establishment of more restricted gateways in northern latitudes, altered deep ocean circulation. These reorganizations promoted the growth of ice sheets during cooler climatic episodes, marking the onset of glacial intervals that would define later chapters of Earth's history. The decline of the Tethys and the ascent of the Atlantic were thus intertwined with the broader transition from a uniformly warm Mesozoic world to a climate characterized by greater contrast between equator and pole. New ocean current systems emerged through this tectonic rearrangement. Thermohaline circulation strengthened as salinity and temperature contrasts drove deep water formation in northern basins. Surface currents traced elongated gyres shaped by continental boundaries that differed markedly from earlier arrangements. The global conveyor of water, heat, and dissolved gases recalibrated itself to accommodate the new distribution of land and sea. In this reorganization, the disappearance of one ocean corridor enabled the rise of another. The Atlantic assumed responsibilities once carried by the Tethys, guiding climate through its own evolving network of currents. The transformation did not occur abruptly, but through overlapping phases of closure and expansion as tectonic forces quietly redefined the architecture of the oceans. Through these gradual shifts, the planet's surface circulation entered a new configuration, one that continues to influence climate and life across the modern world. Far beneath the mountains that now mark the former margins of the Tethys, fragments of its oceanic crust continue a journey invisible from the surface. Once formed at distant ridges and later drawn into trenches, these slabs descend into the mantle along inclined planes, carrying with them basalt, sediment, and traces of seawater locked within mineral structures. As depth increases, pressure and temperature rise steadily, transforming familiar rock into denser assemblages through metamorphic reactions. Water released during these transitions migrates upward, influencing melting in overlying regions, while the bulk of the slab sinks deeper into the convecting mantle. This descent does not proceed indefinitely as intact lithosphere. Over extended spans, the subducted material warms and gradually assimilates into the surrounding mantle, losing its rigid identity and blending into a dynamic interior that circulates heat from Earth's core toward the surface. The mantle itself is not static stone but a slowly flowing solid, deforming over millions of years in response to thermal gradients. Hotter material rises, cooler material sinks, establishing convection cells that power the movement of tectonic plates above. Within this system, recycled oceanic crust contributes chemical heterogeneity to the mantle. Elements once concentrated in seafloor basalts are redistributed, altering the composition of future magmas generated at spreading centers or volcanic arcs. In some regions, portions of subducted slabs may accumulate near the boundary between mantle and core, forming reservoirs that influence mantle plumes rising toward the surface. These plumes, buoyant columns of hotter material, can generate volcanic provinces far from plate boundaries, reshaping landscapes through eruptions that spread basalt across vast areas. Over geological time, the interplay between subduction and plume activity modifies the architecture of continents and oceans alike. As slabs sink and convection adjusts, surface plates respond, initiating new episodes of rifting or altering existing boundaries. The recycling of oceanic crust ensures that Earth's exterior remains in flux, preventing permanent accumulation of seafloor and maintaining a balance between creation and destruction. What once lay beneath the Tethys does not vanish but becomes part of a deeper cycle, contributing energy and material to future tectonic expressions. Through this mantle engine, the disappearance of an ocean extends beyond surface transformation. The closing of the Tethys fed material into convection currents that will influence plate motion for tens of millions of years to come. Mountain belts erode, sediments redeposit, and new basins open, all underlain by processes initiated far below visible horizons. The engine operates without pause, reshaping Earth incrementally through the steady recycling of crust. In this vast circulation, even a vanished ocean continues to participate, its substance carried downward and eventually returned in altered form to the surface it once defined. Stone carries time within it, not as memory in the human sense, but as measurable change locked into crystal lattices and fossil forms. Minerals that crystallized from molten rock contain trace amounts of radioactive isotopes, unstable atoms that decay at predictable rates into stable daughter elements. By measuring the ratio between parent and daughter isotopes in carefully selected samples, geologists determine the age of igneous layers associated with tectonic events. Radiometric dating transforms rock into a clock, allowing the sequence of rifting, spreading, subduction, and collision to be placed within a calibrated framework extending across millions of years. Sedimentary layers, though often lacking minerals suitable for direct radiometric measurement, reveal their age through the fossils they preserve. Distinct assemblages of marine organisms appear and disappear through geological intervals, providing biostratigraphic markers that can be traced across continents. When identical fossil species occur in widely separated mountain belts, they indicate deposition within the same ancient sea. Correlation of ammonites, foraminifera, and other index fossils across regions now divided by oceans confirms that these lands once shared a common marine environment. In this way, The former extent of the Tethys emerges from patterns preserved in limestone and shale. Paleomagnetism adds another layer of confirmation. As volcanic rocks cool, iron-bearing minerals align with the prevailing magnetic field, recording its direction and inclination at the moment of solidification. Because the inclination of the magnetic field varies systematically with latitude, these preserved orientations reveal the approximate position of a rock relative to the equator at the time it formed. By comparing paleomagnetic data from different regions, scientists reconstruct the movement of continents over vast spans. The progressive shift in recorded magnetic signatures within Indian and Eurasian rocks documents their convergence and eventual collision. Modern technology continues this measurement directly. Satellite-based geodesy employs global positioning systems to track the position of points on Earth's surface with millimeter precision. Stations anchored to bedrock across continents register gradual displacement year after year, confirming that plate motion persists today. The measured velocities align with reconstructions derived from magnetic stripes on the seafloor and fossil correlations within mountain belts, uniting present observation with deep time inference. Through these complementary methods, the narrative of a vanished ocean becomes quantifiable. Radiometric ages constrain the timing of basin formation and closure. Fossils trace marine continuity across present landmasses. Paleomagnetism records latitudinal drift, and satellites verify ongoing motion. The evidence does not rely on a single line of reasoning, but converges from independent sources, each reinforcing the others. Within this integrated framework, the history of the Tethys stands not as speculation, but as a reconstruction grounded in the enduring record written into stone. Nothing about an ocean suggests impermanence when viewed from a human shoreline. Horizons appear fixed, tides return with patient regularity, and coastlines seem anchored in place. Yet, in geological time, ocean basins have lifespans, and their existence follows a repeating pattern that unfolds across hundreds of millions of years. The Tethys was one chapter within a larger rhythm that governs the creation and destruction of marine realms. An ocean basin begins when continental crust stretches and fractures. Heat rising from the mantle thins the lithosphere, rifts deepen, and magma ascends to form new oceanic crust. As separation continues, a spreading ridge develops along the widening gap, adding basaltic seafloor that pushes continents farther apart. Over tens of millions of years, the basin expands, currents establish circulation, and sediments accumulate across shelves and deep plains. This phase of growth may persist for a considerable interval, giving the impression of stability. Yet oceanic crust is denser and thinner than continental crust, and it cools as it moves away from the ridge. With time, it becomes sufficiently dense to descend when convergence begins along its margins. Subduction zones form, trenches deepen, and seafloor is drawn back into the mantle. As consumption overtakes creation, the basin narrows. Volcanic arcs rise, sediments compress, and eventually continents that once drifted apart meet again. The ocean closes, leaving behind mountain belts composed of former seabed. This sequence, from rifting to spreading to subduction and collision, is often described as the Wilson cycle, a conceptual framework that captures the natural opening and closing of oceans. The Tethys was not unique in following this trajectory. Long before it formed, older oceans existed and vanished in similar fashion. The Iapetus Ocean separated ancestral landmasses that would later assemble into parts of North America and Europe, only to close during Paleozoic collisions that raised early mountain chains. The Riaik Ocean once lay between Gondwana and other continental blocks before its floor was consumed, and its sediments uplifted. Even the vast panthalassa that surrounded Pangea has been largely replaced by newer oceanic configurations. Each cycle reshapes Earth's surface, redistributing continents and reorganizing climate. Oceans open where crust thins and close where plates converge, not as singular events, but as phases within an ongoing process driven by mantle convection. The average lifespan of an ocean basin spans hundreds of millions of years, far longer than any civilization yet brief within planetary history. Through this repeating sequence, permanence yields to motion, and seas that seem boundless are revealed as transient expressions of a restless planet. The present arrangement of continents suggests stability, yet beneath familiar coastlines, the same forces that closed the Tethys remain active. Along the boundary between Africa and Eurasia, convergence continues at a measured pace, subtle from year to year but persistent across centuries. The Mediterranean basin, descendant of earlier Tethyan remnants, occupies a zone where subduction and collision interact in complex patterns. Portions of its seafloor descend beneath southern Europe, while elsewhere extension opens small basins even as the broader margin compresses. Africa's gradual northward motion shortens the distance between opposing shores. Island arcs within the eastern Mediterranean mark sites where oceanic crust bends and sinks, echoing earlier stages in the life of larger basins. Sediments accumulate along trenches and deform within accretionary wedges, repeating processes that once operated along the margins of the Tethys. Earthquakes trace active faults across the region, revealing that convergence is ongoing rather than a relic of the past. If this motion persists over tens of millions of years, further closure becomes likely. Marine corridors may narrow as uplift progresses, and segments of the basin could be isolated from broader ocean circulation. In time, continental collision between Africa and Eurasia could intensify, elevating new mountain belts while eliminating remaining seaways. The Mediterranean, expansive by human standards, occupies a transient position within a longer tectonic sequence. Beyond this specific region, other future collisions are projected through analysis of plate motion and mantle convection. The Atlantic, presently widening, may one day reverse course if new subduction zones develop along its margins. Continents that now drift apart could converge again, assembling into a new supercontinent whose configuration differs from any previous arrangement. Such scenarios emerge from models that integrate present-day measurements with patterns observed in ancient orogenic belts and ocean basins. Long-term projections of Earth's geography suggest cycles of assembly and dispersal that extend far beyond recorded history. Coastlines familiar today may become inland ranges, while new oceans open in regions currently occupied by land. Climate systems would adjust to altered circulation pathways, redistributing heat and precipitation in response to shifting continental positions. The reshaping of surface features would proceed gradually, measured in centimeters per year, yet cumulative over immense intervals. Within this framework, the closure of the Tethys is neither singular nor final. It represents one completed phase within an ongoing tectonic cycle. The Mediterranean stands as a reminder that oceans can contract as well as expand, and that present configurations are temporary expressions of deeper forces. The same mantle engine that guided India toward Eurasia continues to operate, ensuring that Earth's geography remains in motion long after current maps fade into geological memory. The arrangement of continents seen today is a moment within a longer procession, a temporary balance between separation and reunion. Plate motion has not ceased with the closure of the Tethys or the widening of the Atlantic. The same slow drift continues across every ocean basin, ensuring that the map of the present will not endure indefinitely. Geological models that integrate plate velocities, mantle convection patterns, and the history of earlier cycles suggest that Earth will again assemble its scattered continents into a single vast landmass. Computer simulations projecting hundreds of millions of years into the future explore several plausible outcomes. In some scenarios, the Atlantic continues to widen for a time before new subduction zones initiate along its margins, reversing its expansion and drawing the Americas back toward Africa and Europe. In others, the Pacific Basin contracts further as subduction consumes its floor, eventually bringing Asia and the Americas into closer contact. Though the precise configuration remains uncertain, the pattern is familiar from deep time. Oceans open, expand, and ultimately close as continents migrate across the globe. As convergence proceeds in these projections, new mountain belts would rise along collision zones, while interior regions of the forming supercontinent might experience arid climates far removed from maritime influence. Meanwhile, elsewhere on the planet, rifting could initiate along zones of weakness within continental crust, allowing new ocean basins to form. The birth of such basins would echo earlier stages in Earth's history, when extensions split older landmasses and created fresh marine corridors. In this way, closure in one region coincides with opening in another, maintaining the dynamic equilibrium of the tectonic cycle. Modern coastlines, though sharply defined on maps, are transient edges within this process. Shorelines shift as plates move, sea levels fluctuate, and basins evolve. Cities built along present beaches occupy ground that may one day lie inland within a mountain range or submerged beneath a different ocean. Sediments deposited along continental margins today may become the limestone of future highlands when convergence resumes. The concept of a future supercontinent does not imply catastrophe, but continuity. It reflects the long-term rhythm by which Earth reorganizes its surface. Over intervals measured in hundreds of millions of years, continents assemble, disperse, and assemble again. The continents we inhabit are participants in this cycle, not fixed anchors upon a static sphere. Through sustained motion guided by the mantle engine below, the planet reshapes its geography, ensuring that the coastlines and oceans familiar now represent only one chapter within a far longer tectonic narrative. As marine corridors vanished and stone rose, where water once circulated, life did not retreat, but reorganized. The uplift of the Himalayas and associated ranges altered gradients of elevation, temperature, and moisture across vast regions. Slopes newly exposed to air created habitats stratified by altitude, from subtropical foothills to alpine zones near the highest ridges. Species adapted to these gradients over successive generations, colonizing niches defined by changing climate and terrain. The disappearance of the Tethys did not erase biodiversity, it redirected its pathways. With uplift came the birth of expansive river systems. Precipitation falling upon rising mountains carved channels through fractured rock, gathering into streams that converged into powerful rivers. These rivers transported sediment eroded from high elevations into foreland basins, constructing broad floodplains that supported diverse plant communities. Over time, such systems established drainage networks that reshaped regional landscapes, integrating mountain and lowland ecosystems through the continuous movement of water and nutrients. The elevation of the Himalayas influenced atmospheric circulation in ways that extended far beyond the mountain front. As moist air masses encountered the barrier of rising terrain, they were forced upward, cooling and condensing to release heavy rainfall along southern slopes. This orographic effect intensified seasonal monsoon patterns across South Asia, establishing cycles of wet and dry periods that structured ecological rhythms. Regions shielded from direct moisture experienced contrasting climates, promoting differentiation in vegetation and fauna across relatively short geographic distances. These climatic adjustments fostered evolutionary diversification. Isolated valleys and plateaus acted as refuges where populations could diverge genetically over time. Mountain corridors enabled some species to migrate along elevational gradients, tracking suitable climates as conditions fluctuated. In adjacent basins, sediment-rich soils, deposited by rivers supported forests, grasslands, and wetlands, each hosting communities shaped by both tectonic uplift and monsoonal influence. The interplay between rising terrain and atmospheric circulation also affected global systems. Enhanced weathering of uplifted rock drew carbon dioxide from the atmosphere over extended intervals, contributing to long-term climatic cooling. This feedback between tectonics and climate further influenced the distribution of habitats and the evolution of species across continents. The transformation of the Tethys into mountains thus reverberated through biological networks, altering not only local environments but planetary conditions. In this post-ocean landscape, life adjusted continuously to topographic and climatic change. New ecological mosaics replaced former marine expanses, and biodiversity reflected the complex geometry of mountains, rivers, and monsoon systems. The closure of an ocean became the foundation for terrestrial diversification, demonstrating that tectonic processes shape not only stone and water, but the living fabric that adapts to each new configuration of Earth's surface. A human lifetime unfolds against horizons that appear unchanged. Shorelines traced in childhood remain familiar in old age, mountains seem immovable, and the sea returns each day with the same patient rhythm. Within such narrow spans, Earth conveys an impression of permanence. Change, when observed, feels episodic rather than structural, measured in storms, floods, or earthquakes rather than in the migration of continents. Geologic time operates on scales that dwarf ordinary perception. Processes that reshape oceans and assemble mountains advance in increments too small to register within a single generation. Plates shift by centimeters in a year, coastlines adjust by fractions of a degree in latitude, and sediments accumulate grain by grain. The closure of a vast basin or the rise of a mountain range requires millions of years, intervals that exceed written history by orders of magnitude. Against this backdrop, human chronology compresses into a fleeting moment. Because the pace of tectonic motion is so gradual, oceans feel permanent. Their breadth and depth suggest stability, reinforced by the repetition of tides and currents that appear cyclical rather than directional. Maps printed within living memory show continents in consistent positions, and even detailed satellite measurements reveal movement only when data from decades are compared. The cumulative effects of convergence and divergence remain abstract unless viewed through the lens of deep time. This disparity between human and geological scales fosters an illusion of stability. Landscapes seem fixed because the rate of transformation falls below immediate sensory detection. Yet the same mantle convection that guided the drift of India toward Eurasia continues beneath the surface, operating without pause. Subduction zones consume crust incrementally, ridges generate new seafloor, and stress accumulates along faults. The engine does not accelerate for human attention, nor halt for human absence. Understanding this contrast requires stepping beyond lived experience into measured reconstruction. Radiometric clocks, fossil correlations, and paleomagnetic signatures reveal histories that cannot be perceived directly. Through them, the disappearance of the Tethys emerges not as anomaly, but as consequence of persistent motion. What appears static within a century may prove transitional within a million years. Earth's surface is therefore both stable and dynamic, depending on the frame of reference. For societies anchored to coastlines, the ocean seems eternal. For the planet's interior processes, it is a temporary configuration subject to reorganization. The slow, unstoppable motion of plates ensures that continents will continue to drift. Basins will open and close, and mountains will rise and erode long after present observers are gone. Within that enduring cycle, permanence becomes relative, shaped by the scale at which one chooses to look. Stone beneath an ordinary footstep may once have rested beneath warm, shallow water. Pavements, hillsides, and quarried blocks often originate in sediments laid down within ancient seas, compacted and uplifted through tectonic motion long after the water receded. In many regions that formed along the margins of the Tethys, limestone dominates the landscape, pale and fine-grained, composed largely of the accumulated remains of marine organisms. What appears as solid ground is frequently the lithified residue of shells, coral fragments, and microscopic skeletal plates that settled quietly through water millions of years ago. Cities constructed from this material carry the imprint of vanished oceans in their walls. Limestone blocks used in cathedrals, civic buildings, and homes contain fossilized shells visible upon close inspection, delicate spirals, and ridges preserved within the stone matrix. These forms once belonged to creatures drifting or anchored within tropical waters, yet they now support arches and facades exposed to sun and rain. The transformation from seabed sediment to architectural element reflects the long pathway through burial, compaction, uplift, and quarrying that followed the closure of ancient basins. Along certain coasts, chalk cliffs rise in brilliant white against the sky, their softness betraying an origin in microscopic life. Chalk consists primarily of coccoliths, minute calcareous plates produced by plankton that flourished in warm seas. Layer upon layer of these skeletal fragments accumulated across broad platforms, later hardened into rock and elevated above present sea level. The cliffs that frame modern shorelines are therefore remnants of marine productivity, reshaped by erosion yet retaining the chemical signature of ocean water within their composition. Even inland landscapes preserve similar reminders. Rolling hills, composed of limestone host karst features such as sinkholes and caverns, formed as slightly acidic rainwater dissolves calcium carbonate deposited long ago. Within caves, stalactites and stalagmites grow from dissolved material that once originated as marine shell. In this way, the chemistry of ancient seas continues to influence present landforms through slow dissolution and redeposition. Such evidence rarely announces itself dramatically. It appears in road cuts revealing fossil layers, in the texture of building stone, in cliffs eroded by waves that once shaped different coastlines. The ground beneath daily life holds a stratified archive of environments that preceded the present configuration of continents. Walking across limestone pavements or standing before chalk escarpments involves contact with material that records a marine past. The disappearance of the Tethys did not erase its substance. Instead, it converted water into stone and stone into terrain and structure. Everyday surroundings thus carry subtle testimony to oceans long vanished, embedding their history into the very surfaces upon which modern life unfolds. There is no sound to the closing of an ocean. No single moment announces its disappearance. No audible signal marks the instant when water yields to stone. Instead, the transformation unfolds in a register too slow for human senses, carried forward by forces that operate beneath perception. Across deep time, oceans have opened and closed repeatedly, their cycles layered one upon another like pages in a vast geological archive. The surface of Earth renews itself without haste. Seafloor forms along spreading ridges and travels outward, only to descend again along distant trenches. Continents rift, drift, collide, and rise into mountain belts that later erode into sediment. Rivers transport that sediment toward new basins, where it settles and eventually becomes rock. The same material participates in different environments across hundreds of millions of years, shifting from seabed to summit and back toward depth in a sequence that has no permanent resting place. From a human perspective, such change appears almost non existent. Coastlines traced in memory seem unaltered, and even mountain ranges endure beyond recorded history. Yet within the scale of millions of years, entire oceans can emerge and vanish. The Tethys existed longer than any civilization, shaped climates, hosted ecosystems, and connected distant lands. Its disappearance did not require catastrophe, but only continuity, the steady convergence of plates sustained across immense intervals. The calm pace of geological change carries a paradox. It is gentle in any given year, yet overwhelming in aggregate. A movement of centimeters becomes thousands of kilometers. A sediment layer measured in millimeters becomes a cliff face towering above valleys. The accumulation of such increments produces landscapes that appear monumental and immutable, though their foundations remain subject to further alteration. Deep time humbles by expanding perspective. Millions of years stretch beyond imagination, yet they represent ordinary units within Earth's history. In that span, oceans form, climates shift, life diversifies and reorganizes. What seems stable within a century is provisional within a geological epoch. The apparent stillness of stone conceals motion measured on scales that exceed ordinary experience. Through this lens, the disappearance of the Tethys becomes neither anomaly nor loss, but phase. Other oceans preceded it, and others will follow. The planet's surface remains in quiet negotiation with the mantle below, adjusting through cycles of opening and closure. The silence of deep time does not indicate inactivity. It reflects the measured rhythm of processes too gradual to be heard. Within that rhythm, permanence dissolves into sequence, and the boundaries between sea and land reveal themselves as temporary expressions of a planet in continual renewal. Long before the first cities rose or written language traced memory into clay, the Tethys stretched across the planet as a defining feature of global geography. It endured for spans of time that exceed the entire arc of human civilization, influencing circulation patterns, guiding the evolution of marine life, and shaping the contours of continents. Its waters moderated climates, carried heat between hemispheres, and provided expansive habitats where coral reefs flourished and ammonites drifted. The mountains and deserts that now frame parts of Eurasia and North Africa carry within them the structural legacy of that ancient sea. The Tethys was not erased in a single episode. There was no singular moment when its surface vanished. Instead, it narrowed gradually as plates converged, its floor descending into the mantle while sediments accumulated along collision zones. Volcanic arcs rose, trenches deepened, and fragments of oceanic crust were caught between approaching land masses. Over millions of years, marine basins transformed into folded strata and elevated plateaus. The process unfolded through steady compression rather than sudden catastrophe, guided by forces operating beneath perception. From that slow transformation emerged new landscapes. The Himalayas rose from marine sediment once settled in warm water. The Alps and other ranges folded from carbonate platforms built by organisms long extinct. Regions that were once shallow tropical seas became arid deserts under shifting atmospheric patterns. Climate, biodiversity, and geography were redirected by tectonic motion that never ceased, only altered its expression. This continuity reveals a broader truth about the planet's surface. Nothing upon it is fixed in a permanent state. Continents assemble and disperse, oceans open and close, and climates reorganize according to deep interior dynamics. What appears stable within a human lifespan is provisional within geologic time. The shorelines familiar today will eventually migrate, and the basins that seem enduring will yield to new configurations. The present world is therefore a chapter within an extended narrative rather than its conclusion. The Atlantic continues to widen, other seas continue to contract, and mantle convection sustains the movement that shaped earlier epochs. Future supercontinents will form from plates now separated by water, and new ocean basins will arise where rifts begin. The cycle that governed the life and disappearance of the Tethys persists without interruption. Yet traces of that vanished sea remain tangible. Fossils embedded in limestone, chalk cliffs composed of microscopic shells, and ophiolite fragments perched high in mountain belts all testify to its existence. Beneath towering ranges, former seabed lies folded and uplifted, preserving textures formed underwater. In this sense, the ocean has not entirely gone. It endures within stone, its history encoded in layers that speak of depth, pressure, and time. Beneath the mountains, the ocean still sleeps in rock, awaiting recognition within the quiet continuity of Earth's unfolding story.